Sam, what are you doing? All right, guys, we're gonna get started, but apparently my son decided right now is the time to use the NutriBullet and make a shake. So he's gonna tell me when he's ready and I'm gonna mute it so that it doesn't get too loud here. Are you ready? Okay. I need to get my iPad finishing connecting here. So let me ask if either of you have any questions yet, right yet, before I kind of go into what I was thinking about doing today.
It's mostly like the KSP and the solubility, like the last
Okay.
problem you had where does it precipitate form? I didn't quite get that.
Okay, all right. Yeah, we can go through, I'll actually go through that problem. Even though the key's posted, I'll kind of walk through it. Let's see here. How about you, Sarah? Anything in particular that you're feeling a little bit fuzzy on?
No, I just think a general review of everything would be beneficial for me.
Very good. All right. The iPad is almost connected here. There we go. Oh, I don't know if I had shared with you. I think, Abigail, you were the only one who was with me last week when I was having internet problems. Did I tell you we found out what it was?
Was that like the dog chewing through the wire?
The dog had chewed through holiday decorations outside, and thank goodness it was hooked up to a ground fault interrupter, so that she wasn't getting electrocuted. But oh my gosh, so I'm scared to put out holiday decorations. She did what? Well, we'll see. Okay. Share content. So Abigail, what I'm going to do is I'm going to kind of share some content here first, and then we'll go ahead and get to some of your questions. All right. So what I thought I'd do is just kind of go through this study guide and just kind of give you a perspective, and then highlight that everything we're going to see, whether it's on my practice exam or on Dr. Brown's practice exam, we do tend to see it reflected here, highlighting you're not going to see questions on every single one of these pieces. That would be way too long of an exam, but this is everything that's quote unquote fair game. So let me take a second and kind of go through this. Right, 2 learning units that we have. So it's basically an acid-base learning unit, and then what we're calling sort of complex aqueous ionic equilibria. So that's thinking about mixing acids and bases together to make buffers, then doing battle with those buffers, or considering, doing titrations that actually might make up buffers. That's the last milk. Thank you. Okay, let me know like right when you're ready to blend, and then I will pause. And then, the last thing, that we did in Wednesday's, I guess it was Friday's class after the quiz, and yes, we had some problems on it today, is KSP stuff. So yes, Abigail, I'll go through that one problem that has to do with how do we think about whether or not something will precipitate. I'm going to take a second and kind of go through these skills sort of one at a time. So these were 4 individual lecture periods per learning unit, and then we had a day that we did practice. So we really had 10 lectures so far that we've sort of expanded on this content. You will see some of these are skills that I sort of see as you ready? All right, I'm going to let him make his protein shake. So I'm going to mute just for a second, because otherwise it's going to get too loud. All right, I'll be back.
Yeah, so last milk cold.
All right, thank you, Sam. All right, he's done. All All right, so you definitely are going to see some kind of part 1 type questions that deal with these individual skills. Identifying and classifying substances as weak or strong acids or bases. Being able to write acid-base equilibria and corresponding equilibrium expressions. Ranking acid or base strength if you're given Ka or Kb values. Writing conjugate acid-base pairs. Predicting the net direction of a reaction, knowing that we want to have chemistry happen to generate weaker species, and then all of our around the block calculations. So the good news is I think most of you are really good at a lot of these individual steps because we've had to apply them as we've done some of our more complex problems. But good news is I want to just kind of check off and make sure that these individual things are ones that you're okay with. So we'll see those as we go through kind of the exam key. Acid-base equilibrium problems. I hope, and I think Sarah, you had commented to me, you're like, I think I get this. I see the pattern. This is just the same stuff that we've been doing, but I'm just applying it to a different system. And that's exactly what I want everybody to sort of get to the realization of, is that this is not really anything new. We write a balanced chemical equation, write an equilibrium expression, make sure that we've got everything in the right units, which is going to be either molarity if we're doing an ICE table, or moles if we're doing an ICF table. So when we first started doing in unit 7, we weren't doing battles yet. So there was no chemistry. So it was just an ICE table. So that was the right units of molarity. Solving for X using simplifying assumptions, making sure that we're solving for the correct piece, whether it's H plus concentration, OH minus concentration, pH, so forth. And so our quiz that we had for that was basically after we had learned about salt equilibria. So salt equilibria, weak acid, weak base. So strong acid, strong base, weak acid, weak base, salt. You had to know how to calculate the pH of any of those solutions. And then, you know, the last piece that we talked about, and you're really not going to see a ton of applied stuff with this, but thinking about trends in acidity. Importantly, being able to think about things that are Lewis acids or bases, and then just looking at a molecule maybe that we haven't seen before and using what you know to be able to identify which hydrogen atom might be acidic. So I'm going to pause there for a second, just because that takes us through the beginning, that first half of stuff. That's learning unit 7, and see if you guys have any questions on things there. All right, so moving into unit 8, it really does build on unit 7, right? We're all of a sudden now saying we're going to make buffers by mixing together a weak acid and its conjugate base, or a weak base and its conjugate acid. So that first day, we actually kind of had a laundry list of things that we learned about, whether it was calculations to figure out what volume it would take to get to the equivalence point. Oops, I skipped one. Sorry. Determining protonation state. So understanding if I give you pH and then pKa, you should be able to tell me the protonation state of a molecule. We talked about some qualitative aspects of buffers, such as buffer capacity, buffer range, what would make a best buffer, and so forth. And then we kind of really started talking about the quantitative piece of mixing things together and doing battle with buffers to determine pH. And so that's where we really started layering in. We have to do an ICF table first to do chemistry. And then after that, we can do an ICE table. Or if we know we have a buffer, we can use the Henderson Hasselbach equation. So that was sort of one of the first things too that we learned about in this starting skill from unit 8, is how to think about and use the Henderson Hasselbach equation. Then we had basically 2 days worth of titrations. We had the strong combination, and then we had weak strong combinations, of which there were 2. And that's what your quiz was based on. Okay, is thinking about what's the pH at this point in the titration. So problem solving strategy just continues to build on things that we've been doing. You know, identify who's in solution, you know, eliminating spectators. And then with, you know, most of what we deal with in unit 8, it's doing chemistry first. So that's writing a chemical equation and using an ICF table and moles to keep track of everything. And then after that dust of that battle has settled, then looking at chemical equilibria that are going to have an effect. When we're doing titrations, it's how they're going to affect pH. Abigail, to your point, it's looking at sparingly soluble salts and saying, what are we going to have in solution? Even though this salt, we learned in learning unit 4 that this salt was insoluble. No, it's sparingly soluble. We're going to have a little bit that we can get into solution. Or is that problem that you were asking about? How do we go the other way and say, if I mix some stuff together, what's the possibility of me forming a precipitate? Or am I below the threshold of what I need to get to in order to start precipitating? Okay, and we're going to see that with a problem here. And so that's kind of getting into this last skill, these sparingly soluble salts. So this, and the first 2 kinds of problems we did in class, we didn't get to this predicting precipitation problem in class. So I'll make sure to go through that one fairly slowly. But we've got 2 kinds of problems that are related to things we've seen before. Type 1 problem, where we're going to determine K once we're given equilibrium concentrations. Just kind of giving, after talking to a couple of students today, remember that when we're determining K, when we're doing those type 1 type 1 sort of problems, usually there's something in the problem that's going to be giving us either directly or indirectly equilibrium concentrations. Because remember, we need to have the equilibrium concentrations that we multiply together to give us the K value. So if they give us the pH, that gives us H+ concentration. If they give us the solubility of a salt, that gives us X, right, in our table for sparingly soluble salts. If they give us the percent dissociation, again, that indirectly will allow us to figure out X. So there's lots of ways that we can indirectly get information that will allow us to determine K. The more typical way that we see equilibrium problems is we're using a K value to determine equilibrium values. And for sparingly soluble salts, that means we're going to use a K to determine either molar solubility, that's what X is, or we might ask for what is the specific concentration of a certain species in solution. We talked qualitatively about this concept of a common ion effect. So it's like if you've already filled up your bucket with that ion from another source, you're not going to be able to have your salt dissociate as much. And then this concept too of selective precipitation. Okay, so let's see what else. This is the same. I haven't really changed this from exam to exam, just reminding people about concepts that are emphasized, are listed in bolded text on the previous kind of study guide. And best ways to practice things, look at the in-class problems that we do, look at the problem-solving sessions that we have, go back and look through both sample problems that are listed underneath the Edpuzzle skills videos. These are going to be ones that are listed with asterisks on your skills sheets. So it gives you an opportunity to practice a problem, try it on your own, see a PDF solution. And if you still need some help after that in terms of you don't understand it, there's a video that you can watch that will help you understand that skill. So I'm going to pause there for a second, see if you guys have any questions or comments on that. And then Abigail, I'm going to address your question first about kind of predicting precipitation. And then I'm going to go through my exam. And then if we still have time, I'll go through Dr. Brown's exam and just use it as an opportunity to, I know you guys have the keys for the exam, but sometimes an explanation with it helps it be a little bit more understandable. All right, let me flip over here. Okay, so here's this question, Abigail, that you were probably wondering about. It's like, and I also didn't realize I didn't have an answer, yes or no, in terms of will a precipitate form. In this problem, the answer is no, a precipitate will not form, and I'm going to tell you why here. Okay, so ways to think about this is we need to determine the maximum allowed concentration and then ask the question based on what we have, are we above or below that? So that's a way to think about doing these sort of precipitation problems. So let me walk through this and then we'll see if this makes sense. So how I like to approach these problems is say, well, they gave me the KSP for calcium fluoride, so I can figure out what's the maximum allowed concentration of each of these ions in solution. So how we do that is just like our equilibrium problems, okay? Write a balanced chemical equation, write my KSP value, or this, write my equilibrium expression, which in this case, it's a KSP. Okay, they gave me that KSP value. Third thing is make sure that everything is in the right units. Since I'm doing an ICE table that's starting out with nothing, I didn't have to have anything in the certain kind of units, but I'm going to know that I'm going to get answer in molarity. So I don't start with any calcium or fluoride from any other sources. So when I do my ICE table, I'm going to make a certain amount of calcium ion and then twice as much fluoride ion, because that's how that stoichiometry, that molar ratio works out. So my equilibrium concentrations are going to be X and then twice that. So what I can do is I can put these pieces into my equilibrium expression and solve for X. Now, what's kind of nice about these kinds of problems, there's nothing on the left that says I'm going to have a certain initial concentration that I subtract X from. And so these mathematically actually are a lot easier. We tend not to have to worry about simplifying assumptions, but you do have to make sure that we don't lose track of coefficients that become exponents in our equilibrium expression and become coefficients in our ICE tables, okay? So this is going to end up being 4x cubed equals our KSP value. So I need to divide by my KSP by 4 and then take the cube root of it, and I get x equals 2 times 10 to the minus 4th, okay? I could answer this question by saying the molar solubility of calcium fluoride is 2 times 10 to the minus 4th. That's another way of sort of answering that question, because remember, when we say what is molar solubility, we're really saying what X is. But this problem is asking us, will we precipitate when we're given a certain amount of two species, okay? So what I'm going to do is I'm going to figure out what are the allowable concentrations, the maximum allowable concentrations of calcium and fluoride. So this is just my X value. So the maximum allowed concentration of calcium is 2 times 10 to the minus 4th. And then the maximum allowed concentration of my fluoride is 4 times 10 to the minus 4th. Okay, so what I need to do is figure out, all right, that's the maximum allowed. So what do I have? So I'm going to look at what I have here by taking and recognizing when I mix these two solutions together, I can't just look at this being the concentration of calcium at the end of the day, and then this being the concentration of fluoride at the end of the day, because I mix these two solutions together so they sort of dilute each other. So Abigail, give me a thumbs up if you're with me so far.
Yeah, the dilution thing is confusing me a little bit because I know you usually say never use M1V1 and M2V2 unless you dilute, but like how does that equal?
Yes.
Like how do they dilute each other is what I'm not quite getting.
So we're mixing these solutions together. So if I want to really figure out, all right, let's imagine like I've mixed these together and I haven't yet allowed calcium to find fluoride. In order to figure out, have I gotten above this allowed threshold? Am I more concentrated than this allowed threshold? One of the things that I have to do is figure out, well, what is the concentration of calcium that I have? So in my initial calcium nitrate solution, does it make sense that the concentration of calcium is 0.3 molar?
Yeah.
Okay, now what's happening though is when I mix that with my sodium fluoride solution, I'm mixing 100 milliliters of my calcium nitrate solution with 200 milliliters of my sodium fluoride solution. So by mixing those together, the total volume now in my solution is 300 milliliters. So that extra space, in essence, is diluting my calcium concentration. So my calcium concentration, because I had 100 milliliters of just calcium ion, and then when it got diluted to 300 total, that was a 3-fold dilution. So hopefully it makes sense. That's why my calcium ion concentration is now 0.1 molar. Are you with me?
I think this had been asked before. So why could we not use it for like the other equations of like the weak acids and the bases?
So the time that I told you don't use M1V1 is when we're doing stoichiometry calculations to figure out volume to the equivalence point.
Oh, wait, yeah, that's, yeah, that's right.
Okay, so in some ways you kind of could use it to figure out, you know, some parts of things that we do here, but that was the one time that I said not to use it. So one of the things that we'll see is we've got an excess of calcium here, okay? But what we're going to see here is that our fluoride concentration has not exceeded kind of the allowed amount, okay? Now, one of the things, and actually I'm going to say this here, I've got to look up this problem again, because there's another way that you can think about doing this problem is you can do a Q versus K comparison. Okay, so as I'm thinking through this problem, I had a hard time finding my key for this one when I was making this up to kind of send out to you guys. And now that I'm thinking about it, because what I was just working through this, I was like, well, hey, this is more than it should be, but this guy is less than it should be. So that one, you know, it's like the question is, do you have to have both of them above their threshold? Or if only one of them is above the threshold, but the other one is below, are you still okay? And now that I think about this, I'm going to have to come back to you on this. I'm going to circle back because see if this makes sense. I'm actually going to make myself a new page here. Another way to think about this problem is doing a Q versus K comparison. And when you do Q versus K, you're basically going to take Q is going to be equal to, in this case, it's the calcium concentration times the fluoride concentration squared, but it's using where we're at. And then the K comparison is going to be, it's the same math, but it's using sort of what the allowed concentrations are. Okay, so my K I know is equal to 3.2 times 10 to the minus 11th. So in this case, Q, I might have to take back this key now that I'm remembering and running through my problem here. When I figure out what my Q is, my calcium concentration was 0.1. I'm going to flip back here for a second. My fluoride concentration was 0.04, but I have to square that. So can you do this math for me, Abigail? Can you multiply 0.1 by 0.04 squared?
I get 1.6 times 10 to the negative fourth.
Okay, so I'm going to have to circle back on this. So when I send this video out, I'm going to let people know that I need to circle back on this, because in this case, Q is greater than K, which means we have exceeded, I think, our allowable concentration. And I think that means we're going to form a precipitate. So I have to think about this. I apologize on this. I haven't thought about this for a while. And as I'm looking at this, I was like, oh, the other way you can do this is a Q versus K comparison. But if we do Q versus K, I think since Q is greater than K, we are too product heavy. So we actually have to go back to the left, which actually means we would form a precipitate. So I have to go back. I have to go back and think about this. I don't think about precipitates as much as I think about acid-base stuff. So I'm going to put a pin in this, and Abigail, I'll particularly get back to you, but I'll make sure to send an update if I need to correct this key for everyone. Does that make sense?
Yeah. Yeah,
so
it does.
I think with this one, you actually would form a precipitate, and you can think of it in terms of a Q versus K comparison, or in this case, the fact that you say that if either one of your species goes above its threshold, it's going to allow you to form a precipitate. So, but I want to make sure to confirm that, and I have to find my key for this one. But I think that's going to be the case, that you actually will form a precipitate here.
Yep.
Sarah, any questions from you on this one?
Nope. I haven't seen you use that before with the dilution equation, so that was interesting.
Okay, well, so yeah, and I think Abigail, you might be wondering, you're like, we didn't do that with titrations because when we do titrations, like these are self-diluting. But remember with titrations, we use an ICF table first. So we got to moles and then we need to go back to molarity. So we sort of handle the dilution in that way because we actually had to get to moles and get away from molarity. Okay. All right. So let's talk about some of the problems that you're likely to see. Okay. And I will tell you, I'm not going to change my exam very much in terms of the kinds of problems that you're going to see. So I think my exam and then Dr. Brown has a very similar kind of exam, have a lot of the same parts that you're going to see. So this part one, I'm going to ask you to look at substances and tell me if they're weak, strong, acids, bases, right? So some key things to see here is if you see a carboxylic acid, that's COOH, weak acid. No matter what it looks like on the left side, if you see COOH, weak acid. If you see anything with NH3, okay, weak base, or nitrogen. Now again, this is not going to be something like nitrate, right? That's not going to be acidic, right? So this is going to be a salt that is neither a strong acid or a strong base, okay? But if I had HNO3, that would be a strong acid. So there's lots of different like permutations I can make here. I'm going to encourage people again to go use flashcards that are on Blackboard that will allow you to make sure you know salts, and then weak acids, weak bases, strong acids, strong bases. Okay, so you're going to see a problem like that. You are going to see a problem that's going to ask you to determine whether the pH is less than 7, equal to 7, greater than 7. Or I might ask it, is it going to be acidic, basic, or neutral? Okay. So in this case, this might be reworded and say, if the pH is less than 7, okay, then you need to know that's an acidic solution. Okay. So as a little tip and trick, when you're studying, I usually don't reinvent the wheel when I make a different version for an exam. I ask, how could I ask this question a little bit differently? And I just sort of gave you a little bit of a heads up with this. You could take and say, rather than answering the question with less than, equal to, or greater than 7, I could ask the question with acidic, neutral, or basic. Okay. And then think, how would I have to, if anything, reword these questions or make sure that you could answer these questions using acidic, basic, or neutral? Okay, so a lot of these are sort of a combination of around the block calculations or making sure that you recognize that, okay, if something is a salt in solution and it's not going to have anything that contributes to acid base chemistry, like we see here with sodium nitrate, right? We saw that guy up here, right? That's going to be neutral. So I'm going to pause there for a second, and I don't want to go through and take the time to go through each one of these, but see if you have any questions on any of these.
Oh, wait, I think I did have a question.
Mm-hmm.
So the letter F, the FE, where did that value come from? That's what I couldn't understand. The 3.4 thing?
Yeah, so if you look on my front page for this exam, okay, you're going to see, oh, it might not have been on this page. It might have been something that I sort of provided because I realized it wasn't one of the ones that was listed here, but there is. Iron should have been listed here and you'd get that value there. So that's going to be an acidity value of a metal.
Okay, because when I looked at Appendix C, I couldn't, like I thought I saw the iron 3, but I didn't have the same value, or maybe I was just looking in the wrong spot.
No, and it's possible. Let me actually look up here. I'm going to look at my resources sheet, because it could be that Dr. Parenti, in trying to change her question, did not change. So iron should be 6 times 10 to the minus 3rd. And so what do we have here? Do you hear my deaf cat? He's howling. he can't figure out where everybody is. Yeah. Oh. Now I know what's going on. Sorry, I thought we were looking at a KSP or a Ka value. This is just saying you've got a concentration of iron that's 3.4 times 10 to the minus 1. So you just need to know that, hey, if I have a highly charged metal, that's going to make my solution acidic. That's all that problem is.
That's it.
Yeah. No, this is qualitative, or what we'd say is like maybe semi-quantitative. I wasn't actually asking you to do the calculation to figure out what the pH is. I was just asking predict whether it's going to be acidic, basic, or neutral. And since does that make sense now? And I got turned around by your question too.
Yeah, okay, that makes more sense.
Okay. All right. So you're going to see questions that are kind of like this acidic, basic, or neutral type stuff. Some qualitative questions here. Stronger acid, weaker base, more soluble salt. So this is going to require you to look up stuff that's on a table. And again, it's either going to be, I'll hand you a copy of Appendix C, or more likely you're going to see something like this, where you just have some relevant values that are provided for you, whether they're Ka or Kb values that we see here. Here's KSP values. You've got a periodic table. Okay, so you'll have to make a determination. So let's go through sort of how you do that. Stronger acids are going to have a larger equilibrium constant. Weaker bases are actually going to have a smaller equilibrium constant. So make sure you sort of see what's being asked here. More soluble salts are going to have larger KSP values. When you talk about making a buffer, okay, you want to make sure that you match your species together. Okay, so that's why that guy is the right answer. And then when you're choosing a buffer at a certain pH, you want to make sure that you match the pH that you want to be at with the pKa of the acid. So this guy would not be a good buffer because the pKa of that weak acid is 9.24. So any questions on that first page? All right, second page here, a little bit around the block kind of calculations, right? So there's just a few things here that we have to do to interconvert things. So hopefully we've been doing so much of this that these are kind of pretty straightforward, right? Whether it's using a relationship between Ka, Kb, and Kw, understanding how we think about pKa values from a Ka value is just the negative log of it. pH of a solution that has kind of 0.1 molar concentration of base. So that's kind of a simple calculation with Henderson Hasselbach. And then again, sort of around the block calculation. Okay, so hopefully those are pretty straightforward. And in my key, I think I have a good deal of, rather than just providing the answer on this, on these part 1 questions, which you don't get partial credit for, it is something that I do try to provide kind of some direction to help if you didn't know how that answer was obtained. Kind of some information here about thinking about solubility, right? This is the common ion effect. If we add calcium nitrate, we're going to be adding more calcium into solution, which means we are going to decrease the solubility of calcium carbonate because we're not going to be able to allow as much calcium into solution. Writing conjugate species, hopefully again, some of these earlier pieces are not much that requires explanation on my part. Making sure if you're looking at a certain equation, there's all kinds of different K values that we learned about. So making sure that you could know which K value to use, and then thinking about equilibrium shifting. So this is a little bit thinking about pH and pKa value. So again, I'm telling you the pH that you're at. You might have to look up the Ka and thus the pKa value, and then use that to determine, in this case, molecule is going to win. This guy gets to keep its proton. In this situation, environment is going to win. So that gets deprotonated. Let's see. Then we just have another one where it's just asking you to sort of draw. Okay, any questions on this stuff?
Are we going to have to draw the molecule for the test?
So in this case, I mean, hopefully this is one of those things. If you look at this and I know that this guy, I could look up the pKa of this guy. I know the pH that the problem tells me. So in this case, environment wins, but sort of built into this problem is recognizing that this is the hydrogen atom that would come off. Okay, so in that case, all you do is redraw the rest of the molecule, and I'm taking that hydrogen off. And so when we take a hydrogen off and make a conjugate base, it's going to be negatively charged.
Okay, that makes more sense.
All right. Anything from you, Sarah, on this page?
Nope, I was going to ask the same questions
Okay.
about 6.
Okay, very good. All right. So, and this exam is set up like the last one, where there's going to be a part 2, and then you're going to be able to choose a part 3 question. And the part 3 questions are going to be questions, and again, you'll only do one of them, but it'll be questions like we've seen in the problems that we've done in class. So they're going to be ones that are asking you to maybe put some pieces together and think about things a little bit differently. So let's see, this one is a pretty straightforward problem. I'm telling you, you've got lactic acid. I give you the pKa of it, and I want to know what's the pH of that solution. So this one was a pretty straightforward kind of unit 7 type problem. It's like, what is the pH of this weak acid solution? So is this a problem that either of you want me to walk through? And it's okay too, if you wanted to do this on the test, if I give you a molecule that's kind of like a little bit bigger and you know that it's a weak acid, you can just kind of give it an abbreviation. You could even call it HA if you want, to just know that you don't have to write all the rest of those atoms, because really what happens is you'd have HA in the presence of water is going to dissociate from HA into A minus and then H plus. And if you wanted to keep it as simple as that, that's okay. You don't have to write the whole chemical formula, because remember, these equations and these ice tables are just a way for us to keep track of what's going on. So these problems, do them the same way we've always done them. You're going to write a balanced chemical equation for what's going on. In this case, there's no chemistry happening here. I've just got a solution. I want to figure out the pH of it. It's a weak acid. So even though I have 0.18 molar lactic acid, I don't have 0.18 molar H plus because it's a weak acid. I'm going to make a little bit of H plus, okay, but I don't exactly know how much that is. So we assign it an X in our ice table. Second step is always writing our equilibrium expression. In this case, it's a Ka expression. Set up your ice table, right? Knowing that when we have acid base or buffer chemistry with titrations and so forth, I mean, we're rarely going to have stoichiometry that isn't 1:1:1. So in this case, we're going to use a simplifying assumption to help us solve for X. In this case, X equals our H plus concentration. So negative log of X is going to give us our pH. Okay, and with this problem, everything that's in red here, you can sort of just see how I assign partial credit in this problem, right? You know, a few points for recognizing how to get the Ka value from pKa, points for your ice table, points for solving for X, points for using that X to solve for pH. Okay. Any questions?
Nope.
All right. Next problem is, how do I calculate volume to the equivalence point? Now remember, this is really a stoichiometry calculation. We had problems like this way back on our second exam when we were learning all kinds of different kinds of chemistry, in the context of stoichiometry. We learned about doing chemistry with bases and acids. In this case, we have our weak base, but when we have a weak strong combination, the strong is going to force all of the weak to do chemistry. And so the chemistry for this is NH3 plus H plus, chloride's a spectator ion, goes to NH4 plus. Now I don't need to do an ICF table or anything with this. What I'm really doing is stoichiometry, right? So I know information about, let's see, find the volume of HCl. So I know the volume of NH3, whoops, right here. And I know the molarity of NH3. So that can allow me to then figure out the moles of NH3. I can change who I'm talking about using a balanced chemical equation. And then using the molarity of HCl, I can figure out the volume of HCl that would be required to get to the equivalence point. Okay. And again, to Abigail, to your point, this is where we don't want to be using M1V1. Okay, that's a dilution equation. It would only work in this case because the stoichiometry is 1-to-1, so you sort of get lucky with that. So if you solved this problem and got the right answer using M1V1, I'd take off a couple of points because that's not the right way to do this problem. Okay. So I'd say that this exam is a good representation of the kinds of problems you're going to see. You saw those kind of part 1 questions are kind of testing our basic skills. I'm going to give you a question where it's determine the pH of a weak acid, weak base, strong acid, strong base, or salt. That was kind of like one of our quiz questions. Question here to determine volume to the equivalence point. So that's kind of reminding us how to do some stoichiometry. And then the last question is choosing one of a couple of questions to do. Okay, so the ones that I had here, there was a buffer calculation. So it wasn't even necessarily a titration equation. Okay, and then there was one that was kind of a KSP type equation. Okay, so this this problem, problem 9, is very related to one of the problems like we did in class today, where it was like, hey, this is kind of some unspecified generic acid, and I give you some information of it, and then I have you do battle with that buffer solution. So this is just like the one we did in class. It's not the exact same problem, but it's one where you actually need to use the Henderson Hasselbach equation to tell you what the pKa is. And then once you do chemistry and you figure out what's left, then you can use the Henderson Hasselbach equation to get your pH value. So this is, different system, and hopefully maybe you recognize the similarity between this and the problem that we did in class. So any questions on this one? All right. So, and Abigail, this is a good question to go over because this shows you kind of the same kind of problem that as the one. So as I'm looking at this problem, one of the things that's different with this problem, and I think this is why I like this problem, but I don't like the one that I assigned for us in class today, is this one's pretty straightforward. So let me kind of go through, let's look at the prompt here. It says, does any solid silver chromate form when we have this number of grams of silver nitrate that we dissolve in this volume of potassium chromate? Okay, so 2 ways that you can solve this problem, and that's kind of what I was showing you when we went over this. The first is through what I call the allowed concentration method. So what we do is we go through and we say, if silver chromate is allowed to dissolve, what's the maximum allowed concentrations? Okay, so that's going through and solving for X here. So the allowed concentrations, X is going to be our chromate concentration. And then we're going to have silver be twice that value. Okay. What we can do then is, what I say here with both methods, you actually have to do this calculation for both parts. So this is what's allowed. So now what I'm going to do is say, well, what do we have? Okay. Well, what do we have in solution? I can take the mass of silver nitrate. I'd need to use a molecular weight to figure out how many moles that is. And then I divide by the volume and I get my silver concentration being that value. Okay. My chromate concentration was the one that was provided. Now, why I like this problem better than the one that we did in class is this one, both of these values are underneath the maximum ceiling. So it's obvious. It's like, oh, both of them are below the maximum limit. I'm not going to have a precipitate formed. And we can actually see the same situation when we do Q versus K. Okay. We can put those same values in and we can say, where are we at? Here's what our Q is. Q is less than what our K value is. So I'm okay. I don't need to form a precipitate. I'm under those allowable limits. So no precipitate forms. So it gets complicated when it's like one of them exceeds, but one of them is below. And I got to make sure that I'm right in what we think about. So I'm going to circle back on that guy. But that's why this problem was like that, because there wasn't that ambiguity. Both of them are below. So in that case, or you could do the Q versus K. And in that case, no precipitate is going to form. Okay, so I'm going to pause there because I kind of went through those problems a little bit quickly. I really didn't go through each of the problems, but I'm going to see if you guys have any questions.
No questions. I think I just need to spend some time reviewing so I recognize what I'm looking at when given an equation and I know basically which pattern to plug it into.
Right, right. All right. And it looks like I had some bonus questions. Oh, bonus, let's see, bonus. Find the pH from the solution, question 8, complete the other part 3 question. Okay, so that was just what that was. So again, looking at Dr. Brown's exam, very similar, right? In terms of the scope of questions. He's asking questions. Tell me whether this is acidic, basic, or neutral. Writing conjugate species. So that's what we have there. And just because I want this to be a, even though you guys might not have these questions, to make sure to highlight when people are writing conjugates, okay? If you're asked to write the conjugate base, that means I'm treating this guy as an acid, so I'm going to take off H+. That's how you make a conjugate base. If you wanted to make a conjugate acid, you're going to take the species and you're going to add H+. Now, one of the things that's important when you're adding H+ is you want to make sure that you put it in the right spot. So that hydrogen is going to go on that nitrogen, which is why we draw it like this. We don't say CH4NH2. That hydrogen doesn't go on the carbon. So it's important that we write it in the right spot. Okay. This is talking about pH at the equivalence points, right? So I had questions like this, but they were sort of lumped in the, was it acidic, basic, or neutral sort of things. So this is talking about a weak, strong combination, a weak, strong combination, and then a strong, strong combination, which always has a neutral equivalence point. Okay. So this is asking us to think about, he gives you the pKa of phenol, and then place the following acids in order from strongest to weakest. So my guess is, oh, actually, I don't even think I have this first page here. Do I? I don't think I do. So he's got listed here what these Ka values are. Oh, this is one you actually had to do a little calculation to figure out what the Ka was because he gave you the pKa. And my guess is his front page probably had K values. You guys could probably find those on Appendix C. So being able to rank things from strongest to weakest based on looking at their equilibrium values. So again, very similar kind of scope of questions. I think I had more questions than he had, but similar kinds of questions. Okay. So then he's got some problems here where determine the pH of this weak acid solution. So just like I had mine was lactic acid. So this is determining the pH of a weak acid solution. This is determining the pH of a salt solution. So he has two problems here for determining pH. Okay. He's got a titration problem here. Okay, so in this case, we're having a strong titration. So remember, when you have a strong titration, every single titration we're going to do, you're always going to want to have an ICF table that you do first to figure out after my battle happens, who's left. And then I need to think about what the potential is for those species to impact pH. When you're doing a strong combination, there's no ICE table because what's left, something is going to be in excess, either the H+ or the OH-, depending on where you are in your titration. So that species just represents how you'll determine what the pH is, right? This is just going to be a situation where H+ is in excess. This is the number of moles of H+ that we have. We're going to put it over the new volume to get a concentration. Negative log of that is going to give me pH. Okay, so 3 problems here on Dr. Brown's exam, kind of thinking about how to figure out pH of a weak acid solution. Then we've got a salt solution, and then we've got a titration. And in this case, it's the simpler sort of titration where it's a strong combination. So I'm going to pause there for a second and see where you guys are at. Any questions? All right. Then he's got 2 more problems here. And I think his problems here, he's got a few more problems before he goes into, I think, one where you could pick. So in this case, we've got another weak base problem. So he wants to know, what is the concentration of hydrazine necessary to have a solution that has this pH? So this is a situation where it's a little bit like working backwards, where, well, if we know what the pH is, we can kind of get some of our equilibrium values. So we did a couple problems like this when we had our in-class problem solving session. Okay, so in this case, we know that this is a weak base, so we can write this equilibrium here where we draw and show the base chemistry happening with hydrazine. Okay, and ultimately, this is the piece that we want to know. Okay, we want to know what is the concentration of N2H4 to kind of produce this pH. So the reason that knowing the pH is important is that allows us to determine this piece. So this is one of those kind of working backwards kinds of problems. We did one of those in our in-class problem that we had. Let's see. Then here's a calculate the KSP problem. Okay, so notice that this one too, it says calculate the KSP for this guy. So that's a type 1 kind of equilibrium problem. Now notice this problem says the solubility of this guy is given as a certain value. When it says that, it's basically telling you what X is. Okay, so you could write this problem, right, where we could say that this is minus X plus X and plus 2X. That's a way that you could do this problem. And then this is going to be X and 2X. And now that I know, it tells me the solubility in water is 2.1 times 10 to the minus 2. That's really telling me what my X value is. Okay, remember and I think I mentioned this at the beginning here, but just to kind of highlight again, when something tells us the solubility is, that's telling me X. Now, if I were to say, calculate the KSP for lead bromide, if the bromide concentration is 2.1 times 10 to the minus 2, if I said that this concentration was 2.1 times 10 to the minus 2, does it make sense to everybody that I'm going to have to divide that value by 2 in order to get that concentration? There was a lot of highlighting on there, but does that make sense? It's a little bit different. If I give you a concentration of one species, that's not necessarily telling you what X is. This guy is 2X. So if I told you this concentration, I'd need to divide by 2 to get to my lead concentration. Okay, but when we're doing these problems where we have to calculate K, It could be something where we have to figure out what information is given in the problem and what does it tell us? Does it tell us X? Does it tell us something else? Okay. Questions on either of these two problems? All right. So I think he's got two more problems here, or one more problem here that's got multi-part before he has students then pick one problem to do. So I think, you know, just kind of comparing these two exams, I think I only had like 3 lengthier calculation problems maybe, and I had a lot more kind of no partial credit type problems. But we were asking kind of the same sorts of questions. So let's look at the last problem that he has here. So this is basically doing battle with a buffer. Okay. So it talks about preparing a buffer here, and we want to know what's the pH of that buffer. Okay. So we can use the Henderson Hasselbach equation since we know what the buffer solution is. We know we have a buffer. Okay. Again, whether it's provided on a table or you'd have to look it up, we'd have to look up the Ka value for this weak acid. Okay, because we need to convert that to pKa to be able to use in our Henderson Hasselbach equation. And we have to calculate, now you'll notice here, this is okay that he did this. See if you can follow the logic, because he put moles in here. And some of you might be like, wait a minute, Dr. Parney, you said it's always concentration. See if you follow this logic. If I take the number of moles of base that he has, I'm going to divide it by the same number as I'd have my denominator divided by that number, by the new volume. So it wouldn't be wrong if you did that, but you don't have to do that. Okay, so in this case, you actually could take a ratio of the number of moles and that would still work. But don't worry if you're like, that's a little bit confusing. I want to convert that into concentration. Absolutely, go ahead and do that. There's nothing wrong with that. Kind of make sure that you always have things in the right units. Okay. In this case, you actually happen to have a neutral solution once you have this pH, this buffer. Then we're going to do battle with the buffer. Okay, so in this case, we're going to be adding a strong acid to it. HNO3 is a strong acid. So we want to know what's the pH of the new solution. So we use an ICF table to do battle. And then once we figure out what's left, we really, we diminished our base army. We added to our acid army. And so now we're going to have a different kind of number of moles to have in here. Now, again, if you went and you kind of thought about, and this is why he says neglect any changes in volume. You still could take this if you wanted. Okay, and it says that we have 100 milliliter solution. If you wanted, you could still take these numbers and you could divide by 0.1 to get the molarity. But because I'd be dividing each one by 0.1, mathematically it doesn't matter, which is why we can take a little shortcut here. The only hesitation I have in taking those shortcuts is sometimes students might take a shortcut, like if they were doing another kind of problem that we wouldn't want to do that. So not a problem if you put moles in here, but I just want to make sure that you understand that it's kind of unique to this situation. Then the last part says, as a comparison, what is the pH of if you had this number of moles of HNO3 alone in water? So again, highlighting that when you do this chemistry and you have a battle with a buffer, you don't change pH very much. You take pH from 7 and you go to 6.73. But if you just did that same battle just in water, you didn't have a buffer to battle with, the pH would end up being 1.40. Okay, so questions on this guy? Okay, so Dr. Brown's exam went on then and had 2 possible questions that you could choose from, problems 10 or 11. So we'll kind of look at these each individually. This first one sort of is a titration problem. And this next one is a little bit more complicated because it's asking you to think about diprotic acids. Okay, so let's take a look at these problems independently here. So in this case, we've got a strong base doing titration with a weak acid. Okay, so in this case, we want to know what's the pH of the solution after 20 milliliters of sodium hydroxide has been added. So we always want to write an ICF table and a corresponding chemistry equation to figure out what's going on. So because ICF tables always have moles, and this is how I assign partial credit for problems like these, you always want to take what you have and convert to moles. So here's the number of moles that we have of our weak acid. Here's the number of moles that we have for our strong base. We're always going to have something be strong, and in this case, it's the base there. Chemistry that happens is hydroxide is going to be taking protons away from my weak acid to generate water, which again is not going to be part of the equilibrium or the calculations here. And then we make our conjugate base. So hopefully you can look here and recognize that my strong stuff is my limiting reagent, which means I'm before the equivalence point. I always told you guys, and Dr. Brown does the same, we set up our titrations so that your weak stuff is what you're starting with, and then you're titrating from your burette. Okay, so the fact that my strong stuff is limiting is going to tell me that I'm before the equivalence point. Well, if you remember from doing lots of practice with these calculations, if you are doing a titration and you are of a weak strong combination and you are before the equivalence point, once you figure out the amount of stuff that's left, you've got a buffer. So again, you can put these into the Henderson Hasselbach equation and solve for pH. Whoops, that's pKa. You can put these in and solve for pH. You'll notice he did the same thing here. It's not at all incorrect that he did this. He didn't find kind of the combined volume to get concentrations to put in here, which is totally fine because we'd be dividing by the same number. So mathematically, that's not going to matter. Okay, so that's another one of these problems where it's a titration, but in this case, this was the weak strong titration. That was an option you could do to do that extra sort of problem here. The titration that he had as part of his regular part of the exam was a strong titration. Questions on this guy? All right. Last problem here, and this one's a little bit more involved. So I'm going to take a second and go through this because this is we had a problem like this in our problems that we worked through in class today, where we talked about having a something that was not a monoprotic acid. So mono meaning one, protic meaning proton. Most of the acids that we've worked with and done titrations or made buffers with or anything like that have been monoprotic acids. So when I described to a few people today what we think about with either diprotic, or we call these polyprotic, more than one proton, we can think about them as armies that have layers. Okay, so this, for example, is a diprotic acid. So we're going to have one layer of protons, and when we remove and battle all of those away, there's still another layer of protons that's on underneath. Okay, so this problem tells us that oxalic acid is a diprotic acid, and it gives us both of these equilibrium constants. So if you didn't know this yet, when you're looking at equilibrium constant values, the Ka1 represents the Ka value for the first proton, and then Ka2 represents the Ka value for the second proton coming off. So here's the two different chemistries for what's going on. Chemistry for the first proton to come off looks like this. And then the second proton comes off when this guy now goes and loses his proton. Now, this problem tells us that we really don't need to think about this first proton dissociation because it's telling us it's the second proton that's going to kind of only partially dissociate. The first one comes off all the way. The second one is the one that partially dissociates. Okay. Do you remember when we did problems in class and we talked about what it means when we say something dissociates to a certain percent? That's a way of telling us what X is, okay? This problem is asking us to find pH. So see if you can follow me through this. Now, this is a problem. This is a challenging problem. Dr. Brown and I both give kind of like challenging problems as one of the options. We want to see, can people kind of take multiple things and sort of put them together? So let's follow along here. This is the relevant equilibrium that we're going to be using to determine pH, or to think about. In this case, it's asking us to find pH to the 100th place for a solution. Okay, so here's the relevant equilibrium that we're looking at. Okay, so he didn't necessarily fill out the rest of his ICE table here, but here's what that equilibrium expression is going to look like, right? It's going to be these products over reactants, and we're using the Ka2 value for this. Okay, now what he's choosing to recognize here is when we say that we're 1.5% dissociated. Remember, a percent is always a part over a whole. So 1.5% really represents the part that's dissociated over the whole of what you started with. Okay, so what he's going to do here is recognize that this value right here can get substituted in here. I know that ratio because that's what percent dissociation tells me. It tells me that this part over this whole is 1.5%. Okay, so that being 1.5% means that I now have H plus times 0.015 equals my equilibrium constant. So this is just a way now of solving for what my equilibrium my H plus concentration is. And once I know what my H plus concentration is, then I can get my pH. Okay, those last two problems, well, particularly this last one, I think was a little bit challenging. It asked us to think a little bit outside of the box, different from things that we've normally done. You know, the last part 3 is intended to do that. It's intended to have people think a little bit outside the box. So I'm going to pause there for a second, Sarah and Abigail, see if you guys have any questions on things here. If there's anything else that you'd like me to sort of go over or review with you.
Yeah, so for this last problem right here, the percent dissociation, you're saying that could be a viable challenge problem on the test?
I mean, the challenge problems are always going to be problems like you haven't seen before. I'm sort of asking, like, can people problem solve and take skills that they've learned and apply them in a new situation? Okay, so this happens to be a problem that Dr. Brown chose. I would say the problems that we've done, I can't say every single one of the problems, but the problems that we've done in like our in-class problem solving sessions tend to be ones that ask you to stretch a little bit more. You know, I'm not just saying, okay, here's another version of what's the pH of this salt solution. It's, you know, can we think about doing that? Even if you look at the problems, for example, that I had for these, right? It was kind of problem 9 was one where we did one like this in class. It was like, oh, I kind of had to have 2 parts to this. Sorry, my husband was trying to call. You guys are, oh, John, are you there? Oh, shoot. Hang on, don't, I'm home. Don't, Abigail, don't hang up here. What? I mean, I don't need anything, see you. All right, bye. He knocked me out of my meeting here. All right, you guys are still there. So let me just connect my iPad again. He's usually pretty good. He knows I have class with you guys. And let me just reconnect my iPad here. Abigail, I don't know if that answered your question.
Yeah, because I know that you always talk about how there's usually like a challenge problem or two like thrown into the mix. And so I know the whole point is that we're not really supposed to be expecting it because, it's supposed to challenge
Yeah.
different concepts that we know, but I like to still get a general feel of like what could possibly be on the test.
So, for example, let me just kind of go show you another problem here. This was one of the ones that was on the handout that you had. So let's go to this one here, right? So this one, let me start sharing my screen here. Hang on. Okay. So this is one that asks you to think a little bit outside of the box. Did you look at this problem yet or not yet?
I glanced at it, but I didn't really understand what was going on.
So yeah, let me go through this problem. This problem is like it's a little bit involved, right? So, and I often draw pictures when I'm walking through problems because it helps me sort of try to understand what's going on. So, and this is a real life problem. So when blood is donated, it's a problem if there's too much calcium in the blood, that it can actually trigger clotting in the blood, and then that it makes it non-usable. Okay. So what they do is they treat blood with a sodium oxalate solution to get calcium to precipitate out. So what we have here is we've got a little beaker full of blood here, 104 milliliters of blood. And they tell us that the calcium concentration in the blood is 9.7 times 10 to the minus fifth grams per milliliter. Well, I'm already highlighting that, hey, that's going to be a problem because I need to think about molarity when I'm doing chemistry stuff. So what they do to treat this blood is they mix it with 100 milliliters of 0.1550 molar sodium oxalate solution. Now, the relevant part that we need in there is oxalate, so C2O4. That should have a 2- with there. But what's going to happen is we're going to form a calcium oxalate precipitate. And so the question is, all right, after we've treated this blood, what concentration of calcium is going to kind of remain there? Okay. So conceptually, do you see that that's how we take what's in the prompt and kind of translate it to what's going on here?
Yeah.
Okay. So a couple of things that are relevant here is, like we talked about before, we're mixing two solutions together, so they're diluting each other. And so we're going to have 204 milliliters of solution. And so we're asking, what's the concentration of calcium that's going to remain after we precipitate? So the first thing we need to do is say, well, okay, how many moles, because we're doing battle here. We're doing battle with two things that are going to precipitate. So I need to know how many moles of calcium ion we have, and then how many moles of oxalate we have. Okay. So I can take the concentration that was given to me in grams per milliliter and using the molecular weight. And then I actually don't need to convert to liters here because I need to know moles. I can figure out the number of moles of calcium ion we have. Huh?
What heat?
What kind of pizza is that? Is it, okay, 425, I think. Is that for JT?
Yeah.
Thank you. For oxalate, it's pretty straightforward. They give us the concentration and we know the volume. So this is the number of moles of oxalate we have. And the chemistry that's going to be happening is calcium in a 1-to-1 kind of ratio with oxalate is going to form calcium oxalate as a solid. It's going to precipitate out a solution. With me so far?
Yeah.
Okay. So this is kind of like, the kind of problem that you might see. It might be a precipitation problem. There might be a little bit more of an involved titration problem. I would say it's more likely that the extra problems, like those part 3 problems, are going to be from unit 8, only because we have a lot more applied stuff from there. Okay. So follow with me here. Now we're saying, after this happens, so we're going to have calcium and oxalate doing chemistry. Calcium is going to be our limiting reactant. Hopefully you can see that from when we did this over here. I didn't write it down here, but looking at these two, I definitely have less calcium than oxalate. Okay, so that's going to run out first. So I'm going to have some oxalate that's left in solution. Okay. And you know, the majority of the calcium gets precipitated out as calcium oxalate. But the big question is, does any calcium go back into solution? So what I need to do then is do a little ice table and say, all right, here's the calcium oxalate that precipitated. Is there a little scoop of it that can go back into solution? I don't know. I don't know if animals have been fed. So she's acting like she's hungry. So if you want, go ahead, and I don't think.
Yeah, you can use some meat.
Yep. Sorry, Charlotte needs to eat. So kind of embedded in this problem too is this idea that this is a common ion problem. So when I set up my ice table here, oh, did my Apple Pencil just died? My Apple Pencil may have just died. Had a lot of activity today. When I set up this ice table, I'm going to have a situation where the fact that I've already sort of have some oxalate in solution because there's excess that's there, that's going to mean that even less calcium can come from my calcium oxalate breaking apart. Okay, so I set up my ice table here, and then I'm going to have X and then 0.07475 plus X. Okay, and I can make a simplifying assumption here to make my math easier. So I'm going to say 0.07475 plus X essentially equals 0.07475. Algebraically solving for X here is going to have a concentration of 3.1 times 10 to the minus 8. What's that?
That's reductive effect. I remember walking in on CJ.
Oh, well, then she had to have been fed, but she's fine to eat again if she's hungry. All right, so this is, you know, a little bit more of an involved sort of situation. Another example, just to kind of give you ones I know I've kind of given in the past, is maybe I give you like a lot of hydroxide salts are not soluble, right? So not only might I ask you kind of like, what's the concentration of the metal ion in solution, but maybe I'd ask you for the pH of that solution. And it's like, oh, whoa, that's not a weak acid, weak base, you know, strong acid, strong, it's not like an acid base problem. But the fact that you have a sparingly soluble salt that puts hydroxide into solution sort of allows us to kind of bridge things together. So, you know, I'd say a problem like this is not unfair for part 3. You're going to see some problems that I really want to see who can kind of stretch their problem solving brain. But both Dr. Braun and I have part 1 problems that are really straightforward. And you probably saw from both of our exams, I had more part 1 problems than he did, but I only had like 2 problems that you had to do. And I can't say, I'm not going to say that that's exactly what you're going to see on Wednesday. But it is sort of a mix of pretty straightforward single step kind of calculations in the beginning, then some stuff that it's like based on quizzes, based on, hey, this is stuff that we keep repeating and keep doing. And then part 3 is, let's apply some stuff. Let's solve a problem. Okay, any other questions?
No, I think I'm good.
How about you, Sarah?
Yep, I'm good too. Thank you.
All right, you're welcome, guys. All right, I'm gonna sign off so that I can make sure to get this out there. And we've had a long day of chemistry today. So good work, guys. We'll see ya.